Alrighty, it's 7:30 on a Sunday night, and that means it's time for a little nerddom. Let's just make sure that all the shortcuts work. Yeah, good. We got top of head cam, we've got desktop cam. This is all a very good sign. I'm just gonna double check over here. I had to redo all of my OBS shortcuts because my X keys were acting up a little bit today. So I'm hoping everything will continue to work. I'm just going to try and keep everything in focus the way it's supposed to be. I'm trying something a little different, as we are every time. Like I say, I'm like 90% a making things guy and 1% a streaming guy. So we'll see if, well, as always, we'll see how this goes. Yeah. Let's see. As usual, I hope someone out there in video land will tell me if the audio is bad. But we'll just, for the moment, we'll just sort of get into it. Doing a little, you can sort of see on the widescreen cam up here, what's going on. And I've got my overhead cam at a slightly higher position today. I don't know if that will help us or hurt us, but I figure last time we did this, we were assembling a little tiny moving light. Where did you go, my friend from last time? You are up here in the big bin of things. No. Oh, right, I reskinned you. Yeah, so after last time I did a few modifications to the moving light, including printing out a new shell, and we'll get to that in a second here. But I happened to have some gray PLA that was loaded into the printer at that point, and so I just printed the shell out in gray. So let's look at that. Let me get you a little bit closer here. And actually, well, I think we'll leave autofocus on for now. For some reason, the Logitech camera that I'm using doesn't do great on autofocus. So we'll see how that goes, and if we need to change it out later, we certainly can. I'm gonna move all of these other moving light bits off to the side because we'll look at them in a little bit. Just tidy things up a little bit here. That's a little bit better. So this, oops, put the shell back together. I've left everything sort of naked as we start things off. Kind of nice to have that slightly higher camera, I think, for this, because I think you'll see a little bit better what I'm actually doing, rather than trying to be all close up and soldery about it. So this, here we go. So this is the most recent version of the tiny moving light. Will you focus there, Logitech? You're doing okay. All right, well, we'll roll with that for now. So some modifications have been made since last time, which you probably already see. Some ventilation holes drafted into the top of the PLA body of the moving light itself. And the body itself, I don't know if you can tell, is actually a little bit longer. If I hold it up next to the body we were using last time, in fact. Yeah, so these are the two of the shells side by side there. I've made the sort of nose of it about 5 millimeters longer. And that's just to accommodate a heatsink on the LEDs. So this is the heatsink I've been testing with. Please focus. Focus. This is the heatsink I've been testing with. It's meant for, it's actually out of one of those, like, you know, put a heatsink on your Raspberry Pi so it works better kits that I happen to have lying around. It's like 10 millimeters by 10 millimeters by 5 millimeters, and it does the job pretty well. One of the things that I think we'll find out later tonight is whether these LED stars will, you know, fail if you have zero heat sinking, because the PCBs on them are actually a heat sink in and of themselves. But with the amount of power that I am putting out of them, I think we're going to be more successful with a heat sink on them. But so one of the things we'll get to later tonight is like just going into a little bit of how I picked this particular heatsink, and the process of figuring out like what the heat sinking for some of this is. Other than that, I've made a few of just the physical modifications that we discovered the last time we were streaming. One of which was you know, some things, little things like a slightly larger hole for cables to come out of at the top. And I know I drafted in an access hole there so I could flip that program enable switch that was giving us such trouble last time. And it seems I didn't extrude it, so it didn't actually print out. But that's okay. That's like a 40-minute print, so that'll be a really easy thing to redo. I also modeled a couple other things here. Let me take you out to... There we go. I go to just the wide. Can you see anything? Not really. Oh, it just takes you to blank. Well, that's not as helpful. We can make that better. Just some real good top of my head cam. So there's a 3D printer. It actually sits next to the camera here, and I'm realizing as we start this, I haven't actually popped off my most recent set of prints, so we can do that just here on the world's worst webcam. There we go. Come back to the tabletop here. And back to the wide cam view there. So this is what I designed and printed today. Let's pop these out here. So this is going to be a little mounting hook for the moving light, and I've got a whole float of those just to give them a better chance of working out. And then this is some triangle truss, some like 1-inch triangle truss design. And let's see. I meant to do this before we started things up here, but here we are. In theory, oh, look at that. Look at that. So there is a triangular opening on one side and a triangular sort of proud fitment on the other side. Just there. Let's get that to focus. Yeah. And the two of them fit together in the middle, just like so. And you know, I don't know exactly what we would do to support those two things together. Maybe ultimately this needs, you could glue it, or you know, this could be something a little bit more permanent. But like that, if that's not the world's most adorable piece of triangle truss, I don't know what is. You'll notice it doesn't really have very many cross members. As I was thinking about print orientation for these, I realized that I could have done something like the style of triangle truss that has a sort of a designated bottom section, and then you do diagonals only on the other two sides, and that would have worked okay for the right angle, because this actually prints standing up, sort of like that. So this is the bottom, and it prints standing up this way. So we wouldn't be able to be particularly steep about these diagonals, or it wouldn't print out great. But so far, like that tolerancing is so nice. That's a 0.3 millimeter tolerance all around, which for my printer for PLA is about right. So that should be fun. Well, why don't we, so I think we'll probably move the camera down a little bit, and we'll put a couple of these hooks on, and then we'll hang the moving light on its very own piece of triangle truss for the first time. Won't that be fun? I want to take you back to, let's see, should I take it to wide shot? Yeah. Let's do that so we don't make anybody motion sick while we're moving the other camera. That's a little better. Move the spatula back up, and we'll start putting our little adorable hooks. They're so cute. They're so cute. We'll start putting those in the bottom of our moving light. So I think I'm gonna remove my DMX adapter here, just to make this a little bit easier to work on while it's on the bench. You can hear the sweet, sweet sounds of a jar full of small screwdrivers. And this is a little thing we looked at last time, but I'm doing so much DMX crime. All this is nominally three position terminal jacks and 2 3-pin XLR cables, so I can do sort of any combination of DMX bare wire 3-pin, that I want to do, and over like, a 6 to 8 inch wire length, like that kind of you know, change in impedance isn't really gonna affect things, so I can sort of get away with like doing an actual splitter where normally you wouldn't want to do something like that topology in a real installation. But that's just gonna make this little guy that much easier to work with. And actually, you know what I'm gonna do? I'm gonna just tape this cover on. One of the things I discovered is that the little 2mm screws that I was using, the M2 screws to hold this cover plate onto the base, are crap, I guess, to put it mildly. But they were dirt cheap from Banggood, so I guess it's my own fault, really. But next time, now that I know I'm committed to using them, I'll get them from, you know, Menards or McMaster or some actual reputable dealer, because they stripped out and they're not quite a spec anyway, and so now this is not really, like, I can't affix that top plate onto the base, so for tonight I'm just gonna tape it. I don't think I have all the pieces printed to build another one, including, and they're all in this tasteful silver gray, but I think we're probably not gonna get to that. We spent all of last stream building this one, and then I reskinned, as I mentioned, reskinned this top part, so I don't think we need to spend another stream building another one. They're essentially the same. But what were we... Oh, we were going to put hooks on the bottom. Yeah. So last time, I had put these 2 M3 threaded inserts in the bottom with the idea of adding some kind of to-be-determined hanging hardware. And earlier today, to-be-determined turned into determined, or at least they started to be. This vise is also 3D printed, by the way. This is not at all my own design. This design comes from someone on Thingiverse, which I think... So I did a blog post a couple months back about like the useful 3D printed things that are sort of in my station, and I'm pretty sure that this vise was one of them. So that should be in my blog post somewhere at shameless plug, jeff.glass/blog. If it's working. I had a weird thing happen yesterday. I don't know if there was like a DNS issue or something, but for about 2 hours, I couldn't get to my site, but I could see that it was up using like services like Is It Down for Everyone or Just Me, which is a great resource if you can't tell if a website is really down or you just can't get to it. I typed it in and said, no, your website's fine, everyone else can see it. And then for no explained reason, it came back. So it was all very exciting. I realized before we install these, let's just test the hooks actually, yeah. So that'll hang on there just like that. Step away for a second and grab my M3 hardware bin. I had someone ask me the other day, I think it was the other half of the department where I work, I think it was Alec who asked me the other day, why M3? Like, why metric for all this stuff? And the truth is, I started building out my hardware collection the same time I brought my 3D printer, and all the hardware on it is metric. It's M2, M3, M4, and so I just sort of standardized on some metric parts, and I haven't looked back. So, let's see. I didn't think about exactly what hardware I have when I designed the sort of height of this little member here. I'm hoping that I have the right size M3 screw to go through there and keep that captive. But I guess we'll find out. I think those will work. And these little tiny, like 6mm M3 cap head machine screws. Yes, just proud of the surface there, which I think will be good. So we'll grab that guy. Yeah, I think that's right. And we'll just screw that in. One of the other reasons when I printed out the newest batch of moving light parts, that I did it in gray. I mean, partly I was just being lazy and I had gray in the printer, and so I just did it. But partly I figured it might show up a little bit better on camera, because black on black with black tools, I imagine, is not the clearest thing in the world. Especially if this gets darker for a little bit of focus and get a little more light on this. I don't know. it maybe is not the most perfect thing. But, you know, once again, I'm mostly a making guy and less of a streaming guy. So let's put this other hook on here. And clever bit of design that I was proud of. As I was thinking about how do I, so this is the part itself. You know, I can show you this in Fusion, I think, easier than I can in person. So let's take a look at that real quick. To, of course, open the appropriate design. I don't think there's anything you can't see in here. Triangle truss, moving like case is what this project is called. Yeah, there we go. So let me do a quick rearrange so that I can make sure things are still going well while I'm working in Fusion. Yeah, cool. So this is the part itself, and it mounts to the bottom of the base. Oh, case bottom is the part I'm looking for. Something like that. And of course, I've only drafted one of them here, but it's easy enough to draw one and then just print two of them. But one thing I was thinking about as I was thinking about how to mount this is, so I put a screw through there. How do I tighten it? Well, easily enough. You just punch a hole through the top. And then this doesn't have to be as big as the screw body. It's not like the screw has to pass all the way down through there. It just has to be big enough to fit an Allen key. So I was pretty proud of that solution. All right, let's take it back over to tabletop. Yeah. Top of my head cam. All right, and we'll fit the second hanging bracket on here. The don't know who's out there tonight, but those of you who have moving light experience, so there's a type of bracket. If this was a full-size light, there's an aluminum bracket that mounts to the top of most moving lights with a piece of quarter-turn hardware, and that it takes the 4 mounting points that are on top of a typical light and brings them together into 2 mounting points, and that's what you put your clamps on. And those brackets, I don't know why, are called Omega brackets, typically. I think that's somebody's brand name, but the sort of slang name for them all is Omega brackets. And it sort of makes me think that, like, if they can come up with a name like Omega bracket for what is essentially a piece of aluminum, then I should feel free to come up with a name for these that is equally silly. I mean, J bracket's pretty good, right? J bracket? I'm going to call it a J bracket. Because Jeff Class. The problem I'm having with this one, and I should have seen it coming, so these heat set inserts, these little guys, of which there are 2 in the bottom of this moving light, which you just heat up like we did last time, and you melt them into a hole in your piece, and the knurled bit on the outside sort of melts in. If you don't leave enough relief on the inside here, so this is an unprepared one, so you heat the insert up and you melt it down into that hole. But of course, the melted plastic has to have somewhere to go, and if you don't have enough relief on the inside, what you get is that plastic sort of melts up and over and around and comes back in and fills in the threaded part of your project, sort of exactly the part where you want to thread something in. And I think that's what's happening here. So what I'm going to do to fix that in the long term is to adjust the model so that it has a little bit more space for that spoilage to come up and not get filled by, not fill in the place where the threads are. But for the sake of this evening, I'm going to use some M3 washers. Because I can thread the this cap head screw into position, but just not quite enough for it to sort of clamp down and hold the J bracket in place. So this is one of the nice things about standardizing on a hardware type a little bit, and also it's selfishly like working on projects that are all roughly in the same scale, is that, you know, I have a complete, not a complete set of hardware, but I have M3 bolts and hex nuts and washers and lock washers and a couple different kinds of inserts and lock nuts and wing nuts And so like when problems like this come up, I don't have all of that hardware for every conceivable size, but I have pretty much I have all that hardware for the size that I need. And then this project has actually gotten me to purchase some M2 hardware just because it is so, on such a smaller scale, and we saw how that went. All right, so that has fixed our problem. So it's a little janky with those washers down in there, but that should be okay. Let's put these away, and then let's hang this on some truss. If I'd have thought this all the way through, we could have prepared a little bit of cable and we could hung this up and had a little light show. Maybe we still can, but it feels like a thing I might need another camera for. But we'll get it spinning up anyway. We just might not be able to do it while it's on the truss itself. Okay, so there's that light with the two J hooks on it. And let's see if I can do. Oops, that's me. I don't think there's a good way to do this. This will be fine. Just have to do this a little bit sideways. So that, oh yeah, it's cool. Here, you can look at my face for a little bit. Upside down. How do we fix this? Well, I think we'll just do this sideways. So that's pretty cool. Here, let's put this guy back together for maximum effect. This is one of the another thing I need a little work on is the two parts of this body are sort of just pressure fit together, and the tolerancing is not great. And I have these little tabs to try and compensate for that, but it really needs to be like at least a snap fit, if not a screw. So there is that. Oh, how cute is that? That's little miniature truss. And that's little miniature hanging hardware. How adorable is that? Oh, super cute. Here, now that it's hanging freely, I'm gonna figure out how to do this. I'm gonna flip you upside down and then point you right side up again. Upside down. Right side up. Hello all. I just wanted you to see in all of its hanging glory how adorable that is. How cute is that? Hanging on this little tiny piece of truss there. Ooh, here, for more effect, we'll add another piece of truss. Yeah. So you could hang these on like 3-inch centers and be fine. I was looking at it earlier. So this light, there it is. This light is roughly, so obviously in terms of scale compared to a real light, the ballast part of it up here is huge compared to the light, compared to what it would be in a full size in a full size fixture. The body, though, if you compare this to like another wash fixture, like a VL3500 wash or a Sharpie wash or something like that, is just about exactly in 1:12 scale, like 1 inch is 1 foot scale. And that was my motivation for making this triangle truss, like 1 inch triangle truss as opposed to 1 foot triangle truss. So those are in scale with each other. And then obviously these things are the ballast parts are bigger than they normally would be. Maureen Lottie says adorable. Yay! Isn't it cute? It's super cute. And like these parts 3D print in 45 minutes, so it would be real easy to make like a whole stadium truss of these would be super cute. Well, I think those J hooks are a success. That'll be fun. So let's tip back down here, and then I'm gonna flip you 180 again. There we go. Yeah, great. Well, that's super fun. Yeah, that's super good. So that's basically the progress on these now. I have a new batch of PCBs coming along, so one of the things I identified last time is I use an inductor in the current controller for this that's only rated for 500 milliamps. So I rated the PCB with a component that's rated for 1 full amp. So if I wanted to, I could run this at 1 amp of lighting output. I don't know that I really need to. 500 milliamps is pretty bright. And that actually is going to segue me into the second thing I'm going to do tonight, which is look at some of the new batch of LEDs that I got in just today. Yesterday, because it's Sunday now. So let's grab them. So I have been ordering parts from a website called ledsupply.com. They're based out of, I think, Virginia, and they're great. They ship really fast. Their website is really good. It's really clear. They have links to all of like the Cree part numbers where they actually source things from. So I went on. So when I originally made my purchase, because I wasn't sure if this was going to be the right component, I ordered exactly one of the LED emitter that's in there. And that was a little silly because I've been super afraid of blowing it up. But now that I know it works, I ordered a bunch of things. And I actually have a few more on the way. So these are, they're not exactly the same product. These were some more closeout products that they were offering for sale. And then this was also a closeout project. So these are in the form factor that they call their 3-up, which is 3 of a specific kind of Cree diode on a single aluminum PCB. Focus there. Yeah. And they're all wired in series. They're all sort of circuited together in series. Same with these. So one of these is warm white, one of these is cool white, and I guess we'll figure out which one's which when we turn them on. And then this was a remainder product that I just couldn't help myself. This is a bag of 100 1-up LEDs. In fact, we can break this open and have a look at it. So instead of having those 3 diodes, this is a single diode. Single 7040 Lux Drive Endor. So that's fancy. Here, let's see if we can get it to focus there. Yeah, look at that. It's got a big blob of what looks like epoxy resin over the top of that LED. Maybe for diffusion, I would guess. Because these aren't meant to sort of be beamy fixtures. These are meant to go in industrial applications. And then I also ordered one more of the original emitter that I purchased the first time, just to have around, just in case I fried this specific one and I couldn't make any of these work, I would be able to sort of keep moving. So what I thought we might do is do something. Now we've got, 10, or in the case of our grab bag, 100 of these emitters. It might be kind of fun to characterize them a little bit, because one of the things I've been afraid of, so you may have noticed in the last stream that we did, I took this little guy, and when I was testing him, I only let him be on at, full, or at full 500 milliamps for a matter of seconds. It was sort of ramping back and forth. And that, honestly, it looked cool, and it was the easiest way to test something, but I was really afraid that I was going to fry the one and only set of LED emitters that I had, and then that would have been the end of things. So now I've got a bunch, and I have enough that I could fry one, and one of the things I'm curious about is how much current can I actually put through one of these with no additional heat sinking, and still have it survive, basically. So the LEDs themselves are nominally rated for like maximum current of 1 amp, or the product themselves. So like you see them, they're let me back up. Their luminance is characterized usually at 1 current, sometimes 2. They're characterized at 350 milliamps. And sometimes also 700 milliamps. But the spec sheets say, maximum current 1 amp. I'm not sure where exactly that's coming from, because if you cooled these enough, you presumably could push more current than that through them. But in any case, I have enough of these that I could destroy one now, so I'd like to start by putting, let's put them on a heat sink. We'll run them up to 1 amp, because I know they'll survive 1 amp on a heat sink, they'll just get really hot. And then I'll see... then we'll see how much current we can put through them, not on a heatsink, and have them blow. Kenneth Finnegan is here, and the trouble begins. Fry all of them in one series string at once. Yeah, so I could do that. I don't... Well, I'm sure I have enough power supplies total to be able to do that. I just this week, bought myself a new current limited power supply for my use. I've been making do with a little one that I got at a Hamfest a bunch of years ago that is 30 volts, half an amp, 30 volts, 500 milliamps, an old analog model that I got at this Hamfest. And I finally bought myself a digital one that's 30 volts, 10 amps. So I should be able to, push a bunch of current through these if I really wanted to. But if I was to do these all in series, like each of these individual chips has a forward voltage of like 9 volts because it's 3 white LEDs in series. So if I wanted to do, say, all 10 of my warm white ones and just be done with it, that would be, what, 90 volts DC forward? And I don't have a singular power supply that would do that. I guess I could stack, I have several power supplies I could put in series with each other, but that seems like a silly thing. 120 volt outlet and have a 1N4007 diode. I mean, listen, we're already going to do some kind of silly, maybe smoky things tonight. I don't know that I need to do all of the silly smoky things. Well, let me pop a heatsink back out of storage. And we can start by looking at these in a way that we know won't blow them up. And then we can start blowing them up. And y'all can just enjoy shin cam in the meantime. Let's see. Oh, maybe I have a really conveniently sized heatsink I've been using for this, and I think I just put it back in storage up here. Well, maybe we'll use an inconveniently sized heatsink. Sorry for all the noise. Okay. So, oh, and yeah, I got a little heatsink compound, and do just a little tidying. Ooh, I think I said we were going to look at a little Arduino-controlled light board that I built. Maybe we'll burn some things, and then we can then we'll go back to that. So, ooh, spoilers. Vacuum-fluorescent display. Also, maybe for looking at later. Get this iron out. Ooh, did that? Oh, the cord of my soldering iron landed on my X keys and switch things. Well, that's sort of exciting. All right, why don't we start with the warm white? This is nominally 2700K. Grab a bit of scrap bell wire here. I haven't yet figured out a setup that would allow me to show all the things I would want to show at once. And then it would be great to show, let's show you. Yeah, so you can sort of see on the wide cam here, the world's worst wide cam. You know, I'm working here. I've got the oscilloscope up here that's sometimes good to see. I've got the power supplies here. The shelving is like all up above here. You know, I haven't figured out a setup that really allows me to show off everything. And maybe that's partly because I didn't plan this layout with the intention of filming it. I planned it to be functional for me, which it is. But I think that's making things more complicated. Because there's not, without, you know, having my desk really far away from the wall, I don't see a world in which it's feasible to show, like, my face and the work area from a sort of straight ahead angle. Not that you need to see my face, but, like, that might make it easier to show off some of this from a first person perspective. I don't know. Let's see here. And also, like, when mysterious rustling noises happen, there would be some context for it. Just gonna get a little Q-tip for my flux. Kenneth, are you proud? I got flux. I got too much flux. I have so much flux. but I have it. So let's see. Oh, hey, look at that. It flows much better when you've got flux on it. Amazing. Oops. It also bridges much better. Oh, no. Oh, no, I've bridged it. Oh, no. Well, damn. You know, I'm going to take the lazy way out, which is just to grab another one and flux it up. Solder it again. I don't remember what the story was behind why these were remaindered, but it's possible, just looking, I mean, these ones are still sort of attached to their frame for manufacturing, so I don't know exactly what the story is there. The batch of 100, I think, was used in some project that the manufacturer put out and then removed or something, or was used in a demo fixture or a demo batch, so I expect those to be in a little bit of rough shape. I'm just going to pre-tin these pads a little bit. And then solder 1 wire, solder 2 wire. Okay, finally. So now, I'll take the leads from our power supply. Let's clean things up a little bit here. So that doesn't need to be here. That's fine. That may become useful presently. Stick this to a big fat heatsink. We'll just sort of see that there. And we'll just let that sort of hold itself for now. And then, so this is going to be the other part of this that's going to be complicated, is how do I show, like, there's not going to be, I think, a really good way to show how dang bright this is, because the camera just lowers its exposure until it looks like nothing and the rest of the room looks dark. So I'll also have to do a little narrative storytelling about how bright it's getting. But I'm going to use, these are the leads from my new shiny current limited power supply. I'm just going to throw, well, let's turn it on first. I'm going to turn the voltage all the way down and the current limiting all the way down. Turn that on. And actually, I'll turn my current limiting's on. I'm going to turn the voltage up, and then I can use the current limiting. Yeah, there we go. So that is 200 milliamps, which at a forward voltage of 8.68 volts. And I think the precision on this power supply is plus or minus 10 milliamps and 10 millivolts. So, and not the most precise, but like good enough for the kind of work that I'm going to be doing with it. So that's already, like, it's, again, hard to tell right on a camera, but fairly bright. I'm actually going to throw this over the top of it just so it doesn't blow out the rest of the camera. I'm going to turn up the current limiting to what I've been using, which is 500 milliamps. And now my forward voltage, oops, a little bit high. My forward voltage is 9.23 volts forward across this. And now, like, this is really scorchingly bright. If I take this off, it doesn't look like that much on the camera, but that is painful to look at. And this is with a field of view, most LEDs, these have a field of view of something like 120 degrees. The cool thing about this 3-up product line, because ultimately it's just 3 LEDs on a PCB, except that here, let me block this out for a sec. They manufacture them with 3 little mounting holes that match to Carclow's various optics. Carclow is an optics manufacturer for all kinds of LED-related products, but especially these little guys. So that is the optic. You can see it's just 3 little collimating optics that stick right against that 3-up. And so this one is the like narrow spot lens, but they make a whole variety of them. And actually, I have a couple of them. Maybe we can show those off a little bit. But you can tell. So this is the LEDs. This is fairly bright. I mean, it's painfully bright for me in person. Here, I'm going to turn it off for just a sec so I can see what I'm doing. If I put this optic on here. Ooh, come on. One of the mounting holes is right by where you, by the input leads. So if you're not careful of that when you're soldering them on, then you have to go back and adjust them like this. I do this every damn time. One of the notes I had for myself from last time, from when we assembled the little tiny light, was make yourself a list of the order in which all the things have to happen in order to be successful. And this would be one of the things that would be on those notes, is like, make sure when you're soldering the optic on, soldering the leads onto your LED, that you leave space for the optic to go on. So in any case, so that's the LED with the optic on, and actually you can see similar thing is now in the front of the moving light there. And now, if I turn this on, I'm actually turn my current limiting back down a little bit. And turn it back up. Yeah, so now you've got that really strong beam. I want to say, so the Carclo specs the beam width of these dependent on the actual diode that you're using, right? If it's a, Cree XML white R3000-U2 bin, it'll have this beam angle versus that beam angle. And that's just all to do with the physics of the actual LED emitter itself. Oops, popped up a little bit there. But you can see, if I hold this maybe 8 inches off the deck, how beamy that is off the deck, off of the table, versus how floody. And you can see the reflection, right, obviously, off of my glossy tabletop here. But that's sort of the beam you get with no optic. And then if you install the optic, just how sharp a beam that is, which is pretty cool. And these optics are not expensive. I'm actually gonna douse that again. Like they're $1.50 each in quantity 1. So like a lot if you're using this for an industrial project, right? And you're trying to build 100 of these into a light fixture. But for hobbyists, it's actually really, really reasonable. While that's heating up, because I want to see, it'll get reasonably hot with 500 milliamps. I can show off a few other products. And I've been using this supplier for all of the month, and they seem to have been fine. We have no relationship. I like these products. I think they're cool. So this is another sort of optic. I take it out of the bag. It's another sort of optic that they make for their single emitter LED stars, which is just a singular lens. I think this is the narrow spot. And then for these, you get a holder, something like that. And that would match to, you have your large lens. Again, I think I mostly bought narrow spot ones because that was what I thought I would be interested in. But they fit together. You have a lens and you have a holder, and they sort of snap together there. So when we get to testing the single LED ones, we might play around with that just a little bit. So, but for the moment, we'll pop those back in a bag, and we'll see how hot our LED is getting. So, step 1, this is the LED. I'm gonna take the optic off. I'm gonna leave the optic on, just because it'll be a little bit more close to what we're dealing with in the real life. So right now, the plastic top of the optic is probably 90 degrees Fahrenheit. I can leave my hand on it comfortably and it's fine. The LED star itself is also, I'm putting my finger directly next to the light source here, and I can't feel any residual heat on that aluminum. It's wicking it away just fine. So that's pretty exciting. So now I wonder what'll happen. I'm just going to cover that up again for light's sake. I'm going to dial my current up to 1 amp. Well, let me go. Yeah, 1 amp. So, and you can probably tell from the way the exposure's darkened, I think, that it has gotten significantly brighter. Maybe that's just a trick of the light. But in the room here, it was already painfully bright. Now it's significantly bright. Like I don't want to look at this without some kind of diffusion over the top, because it is seriously punchy. And I'm just going to give that like 30 seconds to heat up, and then we'll see how the heat does. Again, with this heatsink, right? Like this is a big, I'll turn it sideways. A big fatty heatsink that I got from a swap meet ages ago for $1, I think. So that will have no problem dissipating the heat. The question is, can we survive the heat when we only have a little bit of aluminum, or conversely, just a little bit of a fin of a heatsink as well? And if I blow these out, no big deal. All right, so I'm gonna, I think, turn this sideways, and hopefully it won't blind the camera. Oof. That plastic is on the front is probably up to like 120 degrees Fahrenheit. But again, like the aluminum adjacent to I'm touching the PCB under here with my fingers, and I can't feel, ooh, hello. I can't feel any residual heat. So that's a very good sign. So what I'm going to do now, I'm going to turn the light off. And I'm going to give it a moment to cool. When I've been doing this for testing purposes, that's why I brought this fan out. I just blow air across the heatsink just to help cool it off a little bit faster, because take the optic off too. Yeah, that's cool to the touch. Like that's kind of great. I mean, I'm not going to put this size moving light inside of my fixture because the fixture's only that big, but I could. So I was while this cools off, I'll tell you a little story. I was messing around the other day. So for one of the shows that we have going on at my work, we have a bunch of Ayrton Magic Dot Rs, which is a 60-watt RGBW continuous rotation fixture. The head of it is a little globe of the size of a softball. It sits in a yoke, and the whole thing can continuously pan and continuously tilt. And it's a little effects light, and it's a lot of fun. And I was looking at it, I was thinking, how do you get 60 watts? And it's a beam fixture, it's a 2-degree beam. How do you get 60 watts out of something like that? So I was looking into one, and what they have, they have a single emitter RGB-L, compact diode in there, and basically the whole rest of that head is, you split it right down the middle. The front is an optic, right, that gets you your beam out the front, and the back is a heatsink and a fan that cools the whole damn thing off. Everything else is in the base, pretty much. Your ballast, your controls. There's a tilt motor in there, right, just to keep it spinning, tilting. But that's about it. All right, well that's dead cool. So now let's take it off of the heatsink. Actually, here, let me get you a little bit closer. So we can see what happens if it happens. Maybe actually I'll turn it upside down so it points down at the table so it's not quite as blindy. I'm going to turn my current down, turn my power back on. Oops, my current, yeah. So I'm going to turn this up to 500 milliamps. Here we go, 500 milliamps, same forward voltage as before. And we'll do the very scientific test of just waiting till it blows out. See, that's a not inconsiderable amount of light. The nominal lumens of this thing at 750 milliamps of output is comparable to a 75-watt BR20 bulb, like you'd have in an MR16 Birdie or something like that. Not an MR16 bulb, which is pretty decent. That is a not trivial amount of output for a tiny light to have. If I could get this thing to act like a little repositionable Birdie, I would be very happy. Yeah. Well, let's see. How are we doing here? Ooh, whew, smoky. How hot is it, Jeff? It's hot enough that it hurts. It's also I should have taken some of the heatsink compound on the back because it stuck to my finger there while it was very hot. So I wonder if this will burn itself out. Here's my thinking on this, is that it won't, but it will become too hot to be practical. So heat management in LEDs essentially goes like this. It's the same as heat management for any other component. Your electronics, right? In this case, it's the junction of the LED itself, but it could be the junction of a FET or a transistor or something like that, has a maximum temperature before things start to fail. Like the critical bits of the circuit have a maximum working temperature. Here, let's do some scribbling on paper while we talk about this. So the goal, if you want your electronics to survive, and if that's your only goal is for the electronics to survive, you just have to keep the guts of your material below that critical temperature. Ken says, how much does it hurt to touch it now? A lot, I think, Kenneth, I think is the answer. So interestingly, I have my power supply limited at 50 milliamps, and the forward voltage is going down. And we might be able to infer, I mean, not really, but we could infer something about the heat of those diodes by the forward voltage required across them to, to draw 50 milliamps, essentially. And it's slowly dropped. It started at like 8.22 volts. It's now down to 8.13 volts. So in any case, you're trying to keep your, I can smell it. Ooh, I can smell it. Ooh, can you see it smoking? Ooh, I don't know if you can see it smoking there, but it is. What is it that's actually smoking, I wonder? Is it the PCB? Is it the wiring? The wiring is warm, but not noticeably hot. I mean, when you get close to the PCB, it's hot. But something is definitely generating smoke. Trying to figure out how can I shine a light onto the smoke that's brighter than the shiny, the bright thing that I'm testing underneath it. Let's see, you're not going to see that smoke at all. Let's see if I shoot this off camera. Can you? Maybe if I put the optic back on. So now we have the fun challenge. I guess I don't want to melt this optic. I guess I can. I have two more. At least. I have at least two more. Ooh, but I really don't want to touch it. What was this? Was it the flux? It sort of stopped. Oh no, it's still smoking. I was gonna say it stopped smoking, but I don't think that's true. All right, here, let's leave that there in its smoky self for a second, and we'll do just a little scribbling on paper, and then if it survives, we'll jack up the current more and see how we do. Here, let me, gotta be in focus here, yeah. So the maximum junction temperature for this LED, can you see that? No. I'm not touching it, Kenneth. The maximum junction temperature for these LEDs is 150 degrees Celsius. And let's say room temp is 25 degrees C, right? So nominally, I have 125 degrees Celsius. Whoa. Could it be any more of a mess? To work with. Now, 125 degrees C of permissible temperature rise assumes that that I am allowed, that it's okay if this thing gets up to 150 degrees C, well above the boiling point of water, painfully hot. That's just the maximum temperature this thing can be before the LED actually dies, right? So the way that you start working out how much heat sinking you need is to look at some of the characteristics of your device, in this case the LEDs. And for these particular ones, if I'm remembering right, there's a statistic in the datasheet that says that the thermal resistance from the junction, the actual LED junction, to the case, to the PCB in this case, because it's spec'd as a unit, right? From the junction to the PCB bottom is itself, I believe it's 9 degrees Celsius per watt. So for every watt of power consumed, you raise the temperature of the junction of the LED by 9 degrees. Let's see, who's saying things over here? I think the 3D printing case should piece out first temp-wise. Yeah, Kenneth, we're gonna get to that. I've melted some PLA over here. Kenneth, it's not really hot at us. It's just messing with us. Listen. I would love to not have like a star-shaped burn on my hand due to this. How can I show how hot this is? I don't think I can melt solder on it. That would be a little extreme. Maybe I can. That'll sort of put an upper bound on how hot it is if it doesn't melt. Can you see that? Yeah, let's get you over here. Get some additional light so we can see what's going on. Go. Not hot enough to melt solder, which is a good sign. And I don't think it'll be hot enough to melt PLA outright, because PLA doesn't start to get plastic until like 160 degrees C, although I have been wrong before. Let's see, where's a bit of scrap PLA? What can I use here? So let's see here. How do we make this more observable? If I shoot you onto a black thing, that's a little bit better. So if I take this, which is just like a scrap arm from Moving Light Project, let's see if it'll melt. Ooh, I wouldn't say it's not melting. Ooh, yeah. Look at that. Yeah, so that's a problem right there. Is just once it gets hot enough, it'll start melting through the 3D printed moving light, but not rapidly, right? And that was with pressing a little bit hard. And so far, I have been running this little guy at 500 milliamps pretty much continuously, and he's sort of soft fit against that plate in the back there, and so far no visible signs of melting, so that's a good sign. Well, all right. So, shall we jack up the power and then talk some more about thermal resistance? Jeff thinks yes, and Jeff's in charge of this stream. So, let me jack up the power to 750 milliamps, which is the upper range that the luminosity is measured on some of these. Not even all of these sort of 3-up style things. So it looks like I'm doing like thermal resistance ghost stories, like we're all spooky out here now. So the thermal resistance from junction to PCB is 9 degrees C per watt, and I want to say the thermal resistance PCB to air also has a rating. Oh! Oh, you know what failed? I think we melted the solder. We melted the solder on the pads before. Oh, well, and I shorted my power supply. That's all that was. Because I got a little careless with those 2 live wires that just melted off that LED star. All right. Well, that's actually a useful data point, because if this was naked inside the moving light, that's exactly what would have happened, is the wires would have melted off first. Well, so somewhere between 500 and 750, there exists a very practical limit to what we can put on here before the solder melts. I mean, I will try touching it. Ooh, it's not cold. It's hot. That's my very scientific assessment, right? It's hot. It's not screamingly hot. It's not insta-burn hot, but it's hot. So now the question arises, how can I get this thing hot enough to start burning it out? Like, how can I overcurrent this thing? Looks cold now. I disagree, Chris. Still hot. let's see, I would need some way to hold this and apply power to it that doesn't rely on solder. I wonder, I don't know if I have the right, well, I mean, I'd like to have it in free air, but I think we have a way of doing this. So, power supply's off. Let me just shorten these up a little bit here. I'm not going to hold this in my 3D printed vise, which is made out of that same stuff that we were melting a moment ago. That would be a little silly. I am going to, I have a metal jaw just here. I don't think I'll short anything. The other nice thing about this aluminum PCB is that the back is isolated from the front by something. I don't know. I didn't really look at the stack up, but you know, this is not a conductive surface on the back, so you can just mount directly to it, which is awfully nice. But I think that also means that if I do that, if I clip on here and I clip to the back and the front, the solder mask on the front and the aluminum on the back will protect me here. Let's come a little closer. So all right, gonna get real bright. I'm gonna bring you slightly this way. I'm just gonna. As I touched it, I tripped the current limiting, right? It went into current limiting almost immediately. Oh, unless it's toast. Or maybe I am shorting something here. Let's, ooh, it's hot. God damn it. Alrighty. Let's see if I... Ooh, no, it's toast. It's totally toast. I overvoltaged it, and it's totally toast. I don't know if you can see... Here, we're going to have to get you way up and close here. So, when something I did, I either shorted across it, or maybe the power supply is dialed all the way up to 30 volts, right? I just maxed the voltage out and relied on current limiting. So there was a brief second when I put 30 volts across this thing before the current limiting kicked in, and I believe I totally fried it. Let's see, can you see the little tiny light that turns on? There's like one little section of LED that's still LEDing. Will you focus? Will you focus? Here, let me turn off some light. You can see it's too adorable. I have to show you this thing. So the right answer is don't put 30 volts across your LED star that has a forward voltage of like 8 volts. Please focus. Please focus. Please focus. I don't think you're gonna be able to see this. Oh, I don't think you're gonna be able to see this anyway. Turn that voltage down a little bit, huh? Let's like learn from our mistakes. Oh, now it's totally gone. None of it works. All of it is dead. Well, it's not quite what I meant to do. But it was kind of fun. It was kind of fun. We might have better luck with, let's pull out one of the single emitter LEDs, and I'll turn the lights back on. Because, so there's only one single emitter on these other stars, which means the heat load on the PCB will be less, but the local heat load on the diode will be just as great. So maybe we can actually get one of them to burn out. Just mark that up. I remember that it is toast. All right. So there's this guy, the Lux Drive 7040 1-up LED from our friends at LED Supply. Output capacitance, the PSU that killed it. Yeah, certainly. I mean, I had it dialed up to 30 volts. So I had some kind of large capacitor riding at 30 volts, right? And that just all wanted to discharge across that LED right away. So dial up the voltage and then dial up the current limiting, fine. Dial up the voltage with current limiting already set and then touch leads to it, not as fine. This is what we've learned today. Turn that power supply off while we solder these. These also, so as I was saying, like these already have big blobs of solder on them from whatever project they came from previously in the supplier. And this was literally like $10 for a bag of 100 of these. So if this one doesn't work, I won't actually be too sad because there's 99 others that might be just as good. Let's see. We'll just solder this on here. Chris, I think when I posted this the other day, you were the one who asked about why not RGBW, why it was just plain white that I was doing for the moving light project. And I said something, the genuine emitters from the supplier that I have for a single chip RGBW emitter, like 10-watt emitter, is like on a heatsink PCB star is like $15 a piece for each of those emitters, which is like a little bit more than I'm willing to spend at this point in the development for something that like I very well could blow up. But since you asked that, I did a little digging, and online you can get from eBay what claims to be a Cree, RGBW, XML emitter for like $3.50, like $3.50. And I'm really curious what the provenance of those is. I think I might actually have one from a project long ago, but I'm really curious, like, is it genuine? Is it a knockoff? Did it fall off a truck? Like, what's the story there? All right, well, here, let's, as a first test, just so it does survive, let's put this back on our heatsink. And this is the benefit of that isolated back, right? I didn't have to do an isolator between the heatsink and the LED. I can just, slap it on a heatsink and call it a day. So I'm going to turn my current limiting all the way down. Turn this on. Turn the current limiting up. Yeah, there we go. Oop, turn that max voltage down a little bit. So single emitter, right? So, but similarly should have a nominal like max current of like 500 milliamps or something like that. It's a nice color and it's a nice brightness. Like it feels like it's not the same emitter as the warm white we were testing a moment ago, but it's very nice. Let's turn this up to, turn this up to 500 milliamps. Forward voltage like 3 volts, 3 volts at 500 milliamps, like just within the capacity, the measurement accuracy of my little current limited power supply here. That's pretty punchy. It's a good time. I think this is not one of the, zoom me out some, not one of the modules that's meant to go with this particular lens, but let's take a look at it just in case. So, no lens, again, pretty broad. You get that highlight right, of course, off my desk, making it look a little sharper than it is, but, oops, come back. Stay. Not hot, for those wondering. Cold, chilly. All right, lensing. Yeah, so this is meant to go on a, I could be wrong. This may actually work. Oh, it totally works. Wow, look at that. That's a narrow spot. So that is very, very beamy. So that's the narrow 20 millimeter lens from Carclo in its holder. And it kind of, here, I'll take this aside for a sec. It snaps into, see, it's got those 4 little feet there. It sort of snaps into the available holes. Those are notches on the outside of the PCB there, which is kind of a cool way of mounting it. Well, that's cool. Oops, stay. So 500 milliamps on a giant heatsink, fine. I have 100 of these. Should we just go for gold? Let me squirt a little more compound on there because it's tending to lift a little bit. Ooh, a little warm. A little, for those out there wondering what the heat of the hot thing is, a little warm, says science. But really, I mean, like this has been cooking at half an amp for 2 minutes now, and I mean, like it's literally, I could sleep on that. It's cool to the touch. Well, let's, here, I'll tell you what I'm gonna do. I'm gonna turn my fine adjust down. I'm gonna turn my coarse adjust up. I'm going to set this for 1 amp. Ooh, stay. That's going to have to stay down. So now forward voltage is something like 3.23 volts. And we are significantly brighter. Again, I imagine hard to tell on camera, but we are like... Before it was uncomfortable to look at, now it is painful to look at. We are pulling 3 watts out of this emitter. And ooh. It's interesting, kind of like you'd expect, right? The PCB itself, which I'm sure you can't see exactly where I'm touching here. The PCB itself is cool to the touch. If I put my thumb over the diode itself, then my thumb starts to heat up. But that's just how heat do. I'm also looking into this like bright point source is going to make it a little bit harder to read what's going on in the chat comments. Remove heatsink and sleep on it for science. I could do. I mean, it's literally, it's very comfortable. And again, that the PCB is cool to the touch. So this is kind of what I was hoping to get into, right? Is like, we have, not infinite, we have a lot of heat sinking here, plenty of heat sinking. At what point does the LED itself actually fail? And what would contribute to that? If that's the way we're going, just because I don't know, I think it's gonna fail with a whimper rather than a bang. But just in case. I'm going to put on my cool goggles. Ooh. The physical arrangement I have in here makes it mean the wires are trying to pull it up off of the heatsink, which is not ideal because I don't want them to come off the heatsink for any reason. I mean, 1 amp for a couple minutes. The PCB is still cool. Let's jack it up some. Let's go to... I have 100 of these. We'll go to 1.35 amps. Seriously bright. Uncompromisingly bright. Very punchy. The aluminum PCB is starting to get a little bit warm now. But I have my fingers, my other hand here are on the wires that are feeding this PCB, and they're perfectly comfortable. Like, we're not getting the kind of heating of those wires in the solder we were last time. Let's just go for it. That is 2 amps. Not a little bright. Oh, the aluminum's definitely heating up now. Forward voltage 3.6 volts for a white LED. Let's go further. Back off my fine adjust. Let's go to 2.5 amps, 3.7 volts forward. I imagine this doesn't look like anything on camera, does it? Like, you can't actually tell if it's getting brighter because the camera's compensating. This just looks like a bright thing on a desk, I imagine. But it's fun, and my God, it's bright. Ooh, ooh. Heat update. Hot. Aluminum. Aluminum get hot. Can we take it further? 3 amps. So what I'm learning from this, because this is a learning experiment, what I'm learning from this is that with enough heat sinking, anything is possible. Ooh, the wires are getting hot now. Not hot, warm. Ooh, yeah, that star PCB is starting to get a little toasty. Let's just go for it. Let's go. Let me kick up my maximum voltage. 4 amps. Oh, color change. Oh, fascinating. Did you see that? Oh, that was cool. I hope you can see that. Let's cover this up so you can see the color a little better, I hope. So this is a warm white LED, right? I backed it down to 1 amp because I got a little scared. Watch what happens when I crank the current up to like 4 amps. Stay on that PCB. Let's see if you can see this on camera. I'm going to take my glasses off. It goes, can you see that color shift? It looks like a brightness shift on screen, but that is a shifting between warm white and cool white as we go from about 3 amps to about 4 amps. And it corresponds with a real spike in the forward voltage. Like here at, oh, things have changed though. Now we're down at 3 amps and the forward voltage is much higher than it was before. It's like 4.3 volts. I may have damaged something. Maybe not. Down at 1 amp, we're at 3.3 volts again. Let's put those safety glasses back on. Color change. That's fascinating. I wonder what's happening. I mean, what's interesting is like the forward voltage across this diode is shifting. I don't know enough about the science of this to really tell, but like presumably there is a phosphor on top of the light emitting surface. Like most of these warm white diodes, right, are really either like are a UV diode with some kind of either a yellow and a blue phosphor, I think is the most common. And those two things together appear white, and you sort of change how much of each one you have in your, you sort of dope the surface with, and that changes whether your LED looks warm white or cool white. So what I'm theorizing is, so as I apply more current, the voltage drop across the LED is changing, which means that the light that's being output is itself also changing, the color of the light outputted, and maybe that means it's interacting differently with that sort of paint that's over the top of that diode. That's like purely a guess, but I'm loving it. Let's do that one more time. Yeah, look, as I go to now, so here at 3.5 volts, that is now like a neutral white LED color, and my forward voltage, 3.5 amps, neutral white, and my forward voltage is something like 4.7 volts. That's wild. And it's still, you know, I have my finger on it through 2 layers of tissue, and it's a little warm, but like it's still perfectly touchable. This is super fascinating. Let's I mean, do we just crank it? See what happens? I mean, what's the worst? I blow it up and I have 99 more. Are you ready for it? All right, let's do the thing. So 3 amps, 4.5 volts. 3.5 amps, 4.8 volts. 4 amps. Ooh, gone. I've killed something. Kind of fun color effects happening here as I increase the current. But that's it. There's a smell of burning in the air. Not awful burning, but like not great burning. So 4 amps is what I'm learning. 4.5 amps is too much. Really, probably 3 amps was about as much as this could take, because that's about when we started to see that discoloration happening. Neat, though. Super neat. Well, I call that a great experiment. This guy is dead. And not hot. Thanks, heatsink. Fascinating. Oh, super cool. Well, I'm going to do some more reading on that because I want to know what the hell was happening there. It was super interesting. Yeah, cool. We didn't really do that with the others, with the 3-uppy ones, of which I've already killed one, but I have many more. Should we do one more? Here, I'll leave it up to y'all who are here. Should we do one more overcurrent experiment with these, or should we look at the little Arduino light board solution? That one there's not that much to look at, although we could drive the little light around. That'd be kind of fun. More talking about how that setup works, or we could do both. We could overvoltage this guy, overcurrent this guy, and then go look at that one, or look at that one and then overvoltage this one, or we could try playing with the vacuum-fluorescent display and seeing if we can play with that without burning it out, which I'm not 100% convinced I can do. And I only have one of, but I can get more. But that fun might end real quick. Like, that is not a burn it till it burns kind of a fun. That is a one and done, as it were. I can also tell I have like 30 seconds of latency on the stream, maybe like 20 seconds of latency. So when I ask a question, it's like it's sort of like streaming by carrier pigeon and sort of seeing what comes back. Well, while we wait for that, I might as well put some leads on this. You know, interestingly, there is the aluminum block is not hot, but it is warm. It's like 10 degrees above room temp, so this thing was doing its job of dissipating heat. Let's just, as long as we're chilling, let's prep this guy for destruction. We'll see if we can get to overcurrent before we start melting solder on this one. All right, well, let's blur this one up. And we'll go a little bit faster, right, because we know what to look for now. And then we'll look at an Arduino thing, and then who knows. Cool glass is on. Dead LED gone. Heatsink compound. Ooh. Poorly soldered LEDs. We'll just tidy that up real quick. Okay. Ooh, no, come on. One more time. Should probably flux this a little bit since I have it. Kenneth? There was a... Have I mentioned I went to a ham fest this morning? I don't know that I mentioned that. I went to a swap meet this morning. what made me think of it is I'm using my Hakko digital soldering iron. There was a guy selling the Hakko 936 and 926, the old, like, with the analog dial, and I almost bought one. I don't really need one. And the tips were not great, so I would have had to buy tips. Like, it was a whole thing. But I thought about it. This digital one is just the user. We talked about this last time, but the user interface is just not great. All right, soldered up. Time for burning. I'm going to increase my maximum voltage. I'm going to... Oh, should mention, this is the cool white one. So we looked at we killed a warm white one earlier. Let's look at a cool white one and see if similar things happen. Yeah, that's punchy. So these do have a slightly higher luminosity for current. It's like luminous efficiency. Oh, they're really bright. They're also really... It's really purple. I don't know how well that comes across. But you can sort of... it doesn't come across at all. You have to trust me. It's real purple and real punchy. That's 500 milliamps. Crank it up. 1 amp. Let's just coast at 1 amp for a second. Really, I mean, they are super bright. Like, I thought the warm whites are bright. These are punchy. And with an optic on top, it'd be a heck of a thing. Maybe I should consider swapping out the active one in my current demo moving light for this cool white one, because it's... I mean, the CRI is not good, but it is punchy. So, there's that. How are we for heat? Oh, smoke, smoke. Oh, God, smoke. What happened? Oh, it lifted off the heatsink. How are we going to fix that? I think we're going to use a bit of a poker. Okay. So, there we are, back at 1 amp. We're back on the heatsink. Just going to give it a second, make sure it doesn't start smoking. Oh, it's so bright. Let's kick it up another. It's 1.5 amps. I'm going to keep an eye out for more color changes like last time. That makes it only slightly more bearable. 2 amps. Up to 10. So again, so this is the 3 LEDs in series, right? So the forward voltage is multiplied by 3. This is like 2 amps at 9.8 volts. 2.5 amps at 10 volts. 3 amps. Let's compare 3 amps to 1 amp. So 1 amp was painfully bright. 3 amps is unacceptably bright. Like, can't look at with the bare eye bright. That's 3.5 amps. Oh, color change. Yeah, cool. So is the color different here now? I don't think so. Back down to 1.5 amps. So again, I think it's going to be hard to see this on camera, on this camera at least. But as I take it up past 3 amps, as I take it to briefly to 4 amps, it gets cooler. And the forward voltage goes to about 11 volts. So divided by 3, that's like 3.6, 3.7 volts, which is kind of interesting. Let's just take this thing all the way. 4 amps, 5 amps, and we're seriously cool now. I'm going to leave it at 5 amps. I have a feeling I see smoke. Ooh, I got smoke. I got smoke coming off. And it's not just this wooden chopstick that I'm using. Oh, wires are sagging. What's going to go first? The LEDs or the wiring? I'm amazed that the LEDs have held up as long as they have, right? Under 5 amps. I don't even know that they're emitting that much more light than they normally. I mean, they are, but like more than the 3 amp range. I don't know. I would feel like I would need a meter. Oh, it's melting. It's melting real good. Oh man. Decrease my max voltage some. I can smell it now too. 5.5 amps. Now we're really cooking with gas. Something is smoking up a storm. 6 amps? 12 volts, 4 volts forward, and a serious color shift. And brightness shift, right? Like, which again I think must have to do with that change in forward voltage, right? That the frequency of light being emitted by those junctions has changed. We're now up to 6 amps. And a serious amount of smoke. Ooh, we're at the point as I increase the... Oh, yeah, I'm just current limiting. Increase that max voltage a little bit. 6 amps. There it goes. Gone. Voltage limited. Crashed. Yep, that's it. Ooh, one of those diodes went. I have 2 remaining that work. Ooh. Chris, or Kenneth, if you're there, if you had one question about the metal in this project, what would it be in its current state at this current moment? Yeah, it's hot. It's real hot. You can see the smoke. Yeah, it's seriously smoking. It crapped out at like 7 amps, which is amazing. And now, here, I'm going to dial the fine it just down a little bit. You can probably see I only have... Yeah, like that is... I have 2... Woo! That's too... The whole aluminum block is too hot to hold on to at this point. Which is amazing. It really was doing its job. So, let's see. So I had... 7 amps, it died. 5 amps, it was smoking. 4 amps, let's say I could put 4 amps through this and the forward voltage was what, 10.5 volts? So that's 40 watts of consumed power right there, which is how most commercial LED fixtures are spec'd, right? It's not by apparent output power. It's by power consumed by your light source. Chris says, is it sharp? That's a perfect question, Chris, and exactly what I thought you would ask. Yeah, it's the light is sharp. You're killing me, Smalls. In the same way that I am killing LEDs. Yeah, still warm to the touch. Awesome. Well, I feel like we've learned something today. I feel like, I don't know, I feel like I've learned something. Like wow, it's still like uncomfortably hot. Like it's the hot of a shower that you get in, and it's not that it's scalding, but ooh, it's definitely too hot. It's that hot. Oh, yeah, unholdably hot. Half a second is plenty of hot for that hot. Wild. Totally wild. But interestingly enough, the solder didn't fail on this one. Now, and I know on that first one we were kind of floating that chip in space, so maybe that didn't help, that we were putting like extra mechanical strain on that solder joint, and that's what caused it to fail. But like the solder held up just fine, which is pretty cool. Yeah, and so like this, we pushed 40 watts out of this thing ish, right? 4 amps at 10 volts. 40 watts of emitter. So, you know, with a heatsink this size, it's warm. It's definitely warm. Ooh, we could do one more thing. I'm just worried it's going to be unlistenable, which is to do the same thing again with one more diode and put a fan on it. But I just worry that it's going to sound like dookie garbage. Chris says, did the solder fail with a pad? Ooh, that's a fair question. Let's take a look back on that first one that we did, which was this guy. No, it's definitely the solder. The pads look fine. The pads, yeah, the pads are still there. The solder actually failed and melted. But again, remember that was the one that was kind of just like hanging off the end of that, off the end of my vise there. So maybe that had something to do with it. Well, so here's what I would, because we're kind of on a roll, so maybe this is, we just keep going. I would love to try this with a fan. I don't have that many fan options. I have this beefy 120 volt AC muffin fan that would definitely keep the damn thing cool. But I'm worried that it's going to be unlistenable on microphone. So what I think I'm going to do, if you will indulge me, I'm going to turn it on because there's lag. I don't want to have 30 seconds of an unlistenable noise on the stream. I'm going to turn it on for 5 seconds, and then I'm going to work on soldering together a next star while I wait for latency to catch up. And then when it does, you can tell me if that is tolerable for 3 minutes or intolerable and we should do something else. How does that sound? Well, I'm not going to wait for you to tell me how that sounds. You're going to hear how this sounds in 3, 2, 1. So that is the muffin fan on the desk pointing at the heatsink there. And hopefully it wasn't too awful. But like I say, in the meantime, I'm going to put some leads on this guy. And when that lag catches up, you can tell me how that is. I think you're seeing it shortly. In my time, in my space-time continuum. Let's see here. I'm just gonna pre-tin pads on this guy. Fan is not terrible for a short test. For yes, for entire stream, no. That's fair. That's fair. Well, and also, once I've got it stable, I can probably move my body, which has a lav mic on it. I can probably move myself a little bit further from the fan once we get this thing going, which maybe makes this a little bit more acceptable. Well, let's go for it then. So currently, we had started smoking at 5, died at 7 amps. That'll be our sort of high water mark for current on these. I didn't exactly intend this to be like a Destructos event, but I'm kind of enjoying this. Maybe just pivot and become like a, hey, what's up, cool YouTube? Today we're blowing up LEDs here on Destructo channel 3000. Be sure to like, comment, and subscribe. That will never happen. Okay, it's still warm. Still warm. That's wild. I mean, if we're going to go to town, we might as well go in a Lincoln. I do have bigger heat sinks. We lost both cameras? No, we've lost wide camera. Interesting. That's all right. We can go back to, we can go just a full table shot of himself. Let's see. Heat sinks. Yeah, so you don't get Shino-vision as I'm pulling out the heatsink bin. But I don't think that was anyone's favorite part of this experience anyway. Okay. So, you saw this. What I have is that. Ooh. Oh, no, that's still got things on it. Or this. But I think this is going to be our friend. Like the guy that electrocutes himself? Yeah, like the guy who, I'm going to lick a 10 kilovolt capacitor today. Like, you know, good for that person for finding their niche. But like, I think the world needs at most one of that. And it already has one. Yeah, this is still warm to the touch. This is like, I would put this in my pocket on a cold winter day and carry it around for warmth. Warm. That's amazing. That's amazing. Cool. So now we have this guy, another Hamfest find. Maybe I can do this in such a way that it won't try and rip itself off, which would be nice. Let's do just a little. I think this was $1, and I'm about to get my $1 of fun out of it. So it's a CPU cooler, I'm pretty sure, right? It's or something. Big copper surface here, big copper heat pipes, and then I'll terminate inside this finned thing. So I'm going to set this up like this. The fan's going to blow across it like this, and blow across those fins, and hopefully provide a lot of cooling. You know, move the fan back a little bit, get a little breeze up here as well. And we'll just see how we do. Do a little gloop. Do a little, spread that around a little bit. Yeah, let's try and get as much surface area contact between the LED star and the thing and the heat sink itself. I'm really curious what's causing that color change. And I like my theory because I always do, but I don't know. If I wish I had some more science. Oops. Let's see if I can do this so that these just float in such a way that it doesn't try and pull itself off. I think that's gonna stay. Okay. All right. So let's put our tissue of science on top to try and preserve some camera ability, some film ability of this. Tissue of science. Oh, screw it. Do our smaller tissue of science. All right, and we'll start dialing up the current. There we go. 0.5 amp. Works great. I'm going to turn this up. 1 amp. 2 amps. 2 amps, 10 volts. So this is already 20 watts of total consumed power, which is not nothing. Oop, I already have smoke though. That's exciting. What is smoking? What is already smoke? Ooh, I don't know if you can see this. I feel like is the catchphrase of this stream. That little black dot on there, was it some crud? Is it the LED starting to go? I don't know. Let's turn it back up to Ooh. I know what it was. Look at the tissue. I burned a hole through the tissue. So that got a little warm. Probably because it was sitting directly on the surface, whereas previously I've sort of draped it so it's not directly touching. So there's half an amp. There's 1 amp, which does mean there may have been a confounding effect. It may have been that we started to smoke some bits of tissue in previous experiments as well. Try and tent this a little bit. Amazing. I'll take it back up to 2 amps and just see if anything else smokes. All right, 2 amps, 10 volts. Ooh, I have a little smoke. I have quite a bit of smoke. All right, now's the part where you're going to have to forgive me because I'm going to turn this fan on. I'm going to move it right up next to this. Try and suck all that heat away. Try and position this in such a way that you can kind of see what's going on. That better? It's a little better. Just gonna hold that there. All right, so 2 amps, 3 amps. Just gonna dial it down, double check that we're still on the heatsink. We are. Still firmly mounted. It seems good. Okay, dial that back up. Burning the tissues is what I've been waiting for this entire time. Yeah, I mean, that could be like the finale of this thing is we like just put some flammable material on top of these surfaces and just cook things. All right, 2 amps. 3 amps at 10.5 volts. That's 32 watts. Little bit of a color change. Stop my fan from wandering away. Three and a half amps. That's 3.5 amps at 11 volts. 4 amps at 11 volts. That's 44 watts. The lower fins are still cool to the touch. The upper copper is still cool to the touch. Four and a half amps at 11 volts. 5 amps at 11.2 volts. That's 55 watts consumed. It is so bright. With a lens on this? We might have to try and get a lens on this and just shine it about like a flashlight. Should we go a little higher? Not a huge color shift. Yeah, no, for sure a color shift. So I go up past 5.2 amps, 11.3 volts. I'm starting to see that same like cooling color shift. By 6 point... Oh, you know, we're in failure mode now. So what's interesting, what's happening, I dial the current up and up and up, and it got to like 6.5 volts, and then it started sliding back. Let me sure I'm not current limiting, or voltage limiting. Yeah, no matter how high I set the current limiting... Oh, I'm voltage limiting. Ugh, Jeff, don't be dumb. All right, dial it back down. Voltage limit's increased. Dial it back up. 6 amps. 6 amps at 12 volts. Gone. So briefly, 70 watts of output power. But only very briefly. And cool to the touch. So ultimately, Like there is only so. Here, let me kill this. Oh, thank you for bearing with. There's only so fast you can pull that any structure, including this PCB, can pull heat out of the diodes themselves. Right. So, what did we say? It's 9 degrees C per watt from the LED junction to the PCB. And I want to say the PCB to air is something like 6 degrees C per watt. Which means that for thermal failure, we would have something like 7 amps max in air. And we're seeing something like 7 amps failure max on a heatsink, which is interesting. Should we burn some stuff? Should we burn some stuff and then call it a night? I think that's probably what my timeline looks like for this evening. Just gonna burn some stuff and call it a night. So this is toast. Oh, what happened there? There we go. Toast. Toast. Let's do, how many more of each of these have I got? I've got 9 of each. Let's do another cool white. That was pretty fun. We started burning things with like 2 amps directly on those diodes, which seems very survivable for the LEDs themselves. So I think we can burn a good number of things before these things crap out. All right, back onto the heat sink it goes. Probably don't need to turn the fan on this time. I don't think we'll be going to that high of a power. And I'm sure all of your ears will enjoy that. All right, turn the voltage down a little, turn the current all the way down. Go to like 1.5 amps. Can we burn, get my wood stick here. Can we burn paper? Paper is unharmed at 1.5 amps. Go to 2 amps. This is the current where we saw tissue paper burning last time. No dice. These did burn, didn't they? Maybe tissues just burn easier. A little scrap placed directly on the diodes. Let's see if we can get that to burn. While we're in the sort of winding down phase of things tonight, as we just light things on fire, I did want to mention one nifty idea that a friend had this past week, which was he just texted me out of the blue and said, "Hey, think about miniature IQ." So an IQ is an accessory you put in front of a standard lighting fixture. So if this is the nose of the lighting fixture, you set a movable mirror out the front of it that can pan and tilt. The light bounces off that and goes in the direction that you choose. So it gives you sort of a movable spotlight that you can affix to a standard theatrical lighting fixture. His idea was to do one of those, but instead of for a Source 4, which has like a 6¼ degree barrel, do it for a Source 4 Mini that has a 2-inch barrel. And that would be super adorable and not entirely useful. Tissue paper will have a lower ignition point. Chris, of all the people in the world that if I ever needed to answer that question I would come to, it would 100% be you. Ooh, yeah, toasty. I'll bet we can get away with 3 amps without a fan. I'm trying to keep an eye on the tissue paper burning without staring directly at it, because I'm already getting sparklies in my eyes. So to go back to the miniature IQ for a second, so one of the things that I pointed out to this friend of mine who was imagining this miniature moving mirror off the front of a light is that that is not altogether that different from a moving light mechanism, right? It's ultimately just a pan and tilt head that you put a mirror on instead of an emitter. So I think that idea may have legs once this project has sort of gotten to where I want it. We did burn tissue paper earlier, right? That wasn't just like a mass hallucination we had. Yeah, this piece seems to be impervious to heat. Piece of cake. Get some brazing goggles. Yeah. I mean, I kind of need them. Like it's no joke bright. It's seriously bright. I mean, it's not welding bright. Like I'm not getting sunburned, but it's seriously bright. Well, since this isn't catching on fire, which is disappointing in a way that things catching on fire usually isn't, I do want to, well, it might be a little hard to show this, but I think we can figure it out. I do want to put one of my narrow lenses on it and focus all this power, like 40 watts of power, straight in. We might need to do just a little bit of jiggery pokery to make that possible. Let's see. Make a 40-watt flashlight. Tape that. Let's get this set up. Flip 180. Point you at the wall. Just here. Turn off some lights. Turn on some power. Woo! Punchy. Yeah, that's no joke. That's a 30-watt flashlight right there. Awesome. Well, that's a good old time. Flip you back around. What I really need is a button that just flips this so I can do shenanigans when I want to. Interestingly enough, as we're learning about heat sinks, this top portion of copper is mildly warm. These bottom aluminum fins here, noticeably warm. Like, not like burningly warm, but like noticeably warm. Fascinating. Well, good job, heatsink. Chris, I do draw the line at lighter fluid. I do have immediately within arm's reach, I have 91% isopropyl alcohol, which might be kind of exciting. But I think that will probably have to be a project for another time and a less flammable work surface, I would say. Yeah, fascinating. Well, this is cool. This opens up like a whole realm of possibilities in terms of like next steps, because it's clear that even with a little bit of heat sinking, you can really push the boundaries on current outputs on on these biddies. And that's good to know. Like, that opens up some possibilities for the future. Before we go, I will just show off. I won't do too much with, but I did want to show off because I'm proud of it. This the little Arduino-controlled light board, just because I think it's cute. And light board is like a really strong term, but it does work. Here, and I can power everything up, and we can just play with this for a hot second. Square it off a little bit there. Oh, now I have the hanging heart around this, and I don't have a great way to stand it upright, but I think we can just take those off for a second. Actually, it works pretty well. I realized back at the very beginning of this stream, we popped these printed parts off the printer, which is kind of a bold thing to do for the first time live, and I'm just delighted that they work. All right, so let's put this guy back together, and we'll put this guy back together. So I can put DMX into it. And we'll just show them off. Let's see, this is... Are you on camera? There you are. Mini moving head birdie, IQ for source 4. Ooh, yeah, mirror ball rotator. Yeah, Chris, if you ever want to build that mirror ball rotator again, which I know we borrowed for you from Q Brothers last year, and actually we may be doing Q Brothers again this year. But the guts of both the moving light and this control board that I'm going to show off are a little PCB that is a DMX sender receiver. So I think we could build that the receive side of that mirror ball module with a fair amount of ease. Like, we could duplicate it. All that mechanical engineering for all like the gear ratios and stuff, that would still be the same project as it was last time, which was real impressive. But I think this would give us a heads up, or would give Alec a heads up when I make him build it again for us, so we could have our own copy. Okay. So, power up this guy. I've had this power supply for 2 days, and I've already gotten heatsink compound on my leads. I'm not sad about. You stay. I'll see if that stays. So turn voltage down. Go. Turn that up to like 12 volts. So, dirty small, yeah, for sure. So the gist of this control board, like I say, it's probably coming toward the end of my night, so I'll make this pretty brief. But the gist of it here is you have 3 potentiometers, and here, maybe I can arrange this a little better. You can actually see what's going on. Yeah, so stay. 3 potentiometers. Amazing. I did say that was a problem. I'm just going to tape these together for tonight. And all the Arduino is doing on the circuitry side is, well, it's actually doing a little bit of fanciness now. So it's reading in the analog. So the pots are going, 0 to 5 volts on either side, and the wiper's connected to a signal pin. An analog pin on the Arduino reads that signal pin, which gives it an ADC value between 0 and 1023. It then, so the naive implementation was it was mapping that into the range 0 to 255, which are possible servo values, and then writing that directly out to the servo. And what I found was, like, the readings from these pots are not entirely, they're old crappy pots, and they're not entirely consistent. So what it's actually doing is it's taking a reading currently every 20 milliseconds, and it's averaging the last 10 readings to give it its current value. So that helps to smooth out a lot of the jitter that I saw the first time I turned this on. But ultimately, it really is just mapping, you know, those values to the three parameters of this light, which are pan, tilt, and intensity. So let's see if I can I? That's as far as you pan. Let's turn this around. So for reference, so this set of LEDs is set up to max out, or rather the driver is set to max out at 500 milliamps at what, 9.5 volts. So 5 watts LED emitter power compared to the 40 watts we were looking at earlier. So it doesn't, if you'll forgive me, it doesn't really hold a candle in terms of brightness to what we saw earlier. But reasons for limiting it. So one being the little tiny heatsink that's inside there, right? Which may or may not be an issue. The reason that this circuit is limited to 500 milliamps is twofold. To answer the question in two different ways. One is the driver chip in here, the AL8860, I think it is. The 8SoC version maxes out at 1 amp. And the inductor that I chose to go with it, because essentially it's a buck converter that takes your input voltage and bucks it down with your LEDs as part of the feedback path. And so it basically does current limiting in your buck converter to make sure that the average current across your diodes is what you want it to be. The inductor that I chose to go along with that buck converter has a maximum current of 500 milliamps. And the way that you set the maximum current coming out of this is with a set resistor value, which I think is 1 divided by the, let's see, how does this work out? 1 divided by the set resistor value gives you your maximum current. Oh no, 0.1 divided by your set resistor value. So I currently have a set resistor value of 0.2 ohms. It's 2.1 ohm resistors in series, which means that my maximum current is 500 milliamps. I mean, it's still punchy, don't get me wrong. It's, I would say, it's not quite birdie bright, but this is a relatively cool emitter, and I would say it's birdie bright with a cut of Li 201 in it. But yeah, that's the gist of it. I mean, the Arduino is not doing any fancy heavy lifting other than this like averaging that it's doing. But you know, you think about it. I take this off. So what we have here, the big components of this, XLR output connector, right? Potentiometers for input. This is an FTDI converter that I use to program it, which at the moment I'm just using to provide power because I'm lazy. So the whole processing unit, the DMX reception, right, and the Max 485 driver is all contained within this little section. So Chris, going back to that mirror ball rotator, this is essentially the brains of the unit, right? And then all you would need is the continuous rotation servo and your gearing, and that's the full size of the thing. And what I'm excited about is that this module that I've sort of built for myself is now a generic DMX receive and or DMX transmit module that I can use. Like literally this same shield or this same circuitry is what's driving the moving light. The moving light PCB has a little extra sort of 1/2 inch on the side that has the power input for the LED because it has a larger power input, has a voltage regulator. Here, we can, what am I doing? We have a computer. We can do science. Let me fire up Eagle, and I can just show you the difference rather than sort of talking about it. I guess I don't need my safety glasses anymore. Now let's see if I try and transition this to Eagle. No, it thinks it's Fusion. Well, let's make it Eagle. Kill that, and we'll capture. Sorry, streaming on stream. Schematic. There we go. Send to bottom. There we go. We'll just shrink that a little bit so it's a little more visible. Oh, shrink that a little bit. Not perfect, but I think it'll do. So let's look at the board here. Yeah, so this here is our, oh, you can't see the board. Oh, gosh darn it. Let's see the board. There it is. Whew, finally. So this is the version 2 PCB, I should say. So not exactly what's in the moving light at the moment. You still see over here? Oh, right. Unplug DMX. Yeah. The version 2 PCB, right? So this inductor got a lot bigger. So I had to reshuffle some of these components, and I changed the Schottky diode, but I didn't change footprint. So really, it was replace this component and shuffle some things. But the sending circuitry is literally identical to just this half of the board. And in fact, I designed, so like it's all of this and none of the other. In fact, I designed and tested this first, made sure that was working on transmit and receive, and then sort of added this on as supplementary circuitry. And all it is, it's 2 pairs of 3 pads for input, bias resistors. This is the Max 485, right? Your RS485 sender. It's got 2 pull-down resistors on the send and receive line so it doesn't activate on its own, some bypass caps, and a switch that allows you, so if you're receiving DMX, which for the programming that I've got in it now abuses the inbuilt Arduino send and receive functionality, this switch allows you to cut off incoming DMX from coming into the Arduino, so you can cut off and then program it. If you try and program it while there's DMX coming in, things don't always go great. Yeah, I'm gonna take us back to tabletop. So I think that this module has some possibilities, right? Like when I finished the light yesterday, day before, whenever that was, and I was like looking for a way to test it, I was like, oh, I didn't bring a home source of DMX. I could have stolen a Nomad key or figured out something to do. And then I thought, well, I have a generic DMX transmitter. I can do something. And so I whipped this together in like 20 minutes with 3 potentiometers and some code, and now it's a DMX control service. So which also means that anything can be a direct DMX control surface, right? Any kind of switch, any kind of closure or touch sensor, the sky is the limit there, which maybe leads to some fun possibilities. This has been on at full for a few minutes. It's noticeably warm, but the ventilation is actually doing its job. The bottom, because there's similar, I can show you, there's similar slots on the bottom of the unit here. These sort of ventilation holes, right, are fairly cool, and it's all just hot air is passing up through the unit and coming out to the top by convection, which is what I had hoped would happen. So that's pretty cool. Yeah, that's pretty cool. I think I've said that this is going to be winding down the night about 3 separate times now, but I think legitimately this is probably winding down toward the end of my night. So thank you all for joining me as I didn't burn myself once, and I scared myself with sparks only twice, and we burned some tissue paper, and we investigated some weird properties of LEDs, right? That color shift in those LEDs is fascinating. Fascinating. Yeah, I really want to know what's going on. And we burned out 4 sets of LEDs over the course of the evening, so I only have 119 left to play with. But I feel pretty good about that. That was sort of the point of, as my mother used to say, once you have a lot of something, it's a project. And I love that philosophy, right? You get 100 ping pong balls, and suddenly you can do things with them. Or you have, you have 1,000 Post-it notes, and you can do wild and malicious things with them. So now I've got 100 of these LED emitters, and a couple dozen of the 3-up ones, which are super punchy. So now it's just time to have a good time. So, yeah, I'm going to leave it at that. Thank you so much for hanging out with me on another Sunday night here. Things coming up next, possibly another Arduino control surface, When the new version of the PCB comes in, we'll be building a 1 amp version of this, which would be a 10 watt miniature moving light, which would be kind of exciting. We'll be reprinting some of these things to incorporate the newest changes in the case design, and hopefully printing a few more things and continuing to refine the truss design that I put together for the first time today. But until then, have a wonderful evening, and I will see you next time.